Hello, tonight we're going to look at topic 3.14, polar function graphs. We studied in our last lesson polar coordinates. We learned how to do and plot polar coordinates, how to convert between rectangular and polar coordinates and vice versa. And we looked at what would a polar coordinate look like in a complex number system with our eyes. So now that we've learned about that and we've explored how those polar coordinates work, our next step then is going to be looking at polar functions and their graphs. So we need to have a pretty good grasp of the polar points to be able to work in the polar graphs. Polar functions are like other functions that they have input and output values. The input value is going to be given by theta, and that's going to be your independent variable. The output values are going to be given by r, which are going to be your dependent variables. On the AP exam, you're going to need to get used to the phrasing that you might see so you're comfortable with that. So here's an example of what a question or how a question might read. The graph of the polar function, and then notice it has r equals f of theta. So our equation now will be r equals, and then it'll give you a function. So notice the function looks normal. That looks like a sine function. So this is the rectangular equation, and we use the rectangular equation to help us get the polar equation. And this sine function is going to be shown in the polar coordinate system. So that's the round one for 0 to 2 pi. So a few characteristics and words that I want to make sure that you know so you're not surprised if you happen to see them. When we're talking about the rectangular system, we're going to have a positive x-axis and we're going to have the origin point, which is in the middle of the graph. When we're talking about polar graphs, the term positive x-axis, that's your polar axis, and your origin is called the pole. That's the dot in the middle. They have specific symmetry, and this can help us narrow things down. So if it has symmetry or is symmetric with respect to the pole axis, then it's going to be a cosine equation. If it is with respect to the pi over 2 axis, then it's going to be a sine equation. So knowing the symmetry and being able to determine the symmetry can help us understand the graph itself. So that's what my note is over here. It's very common for polar functions to be displayed and use the symmetry. We can use that symmetry to understand the graph and the symmetry within the graph. So that can help us quickly and easily sketch pieces that we need to know. So just so you're familiar with those words, okay? The first thing we're going to look at are graphing the polar function. And a couple of things that you want to be mindful when you're graphing a polar function, and this is really kind of important when you think about it, but graphing a polar function, we always graph counterclockwise from the pole axis. So when we start a graph, we're starting here and then we're going around clockwise. So that's a kind of an important thing to remember when we're graphing these functions. So we always start at the positive x-axis or the pole axis, which was over here. And then when we graph, we go around the circle this way. Okay, so that's important to make sure we're mindful that we know we're going counterclockwise. It's always a good idea to create a table of values when you're trying to graph. You need points to plot, and it's a good strategy, especially when you're attempting to graph things that are new or unknown to you, and we haven't graphed polar functions before, so this is a good example of that. And we're going to utilize this strategy among a few other things to help graph a polar function. All right, so this first example, let r equals f theta, where theta is defined as 3 minus 3 sine theta. So that was that wording we were talking about. It's telling you right here that we're going to be using an r equals equation, and then it's telling you right here that this is what the rectangular equation is going to look like. And then it's going to say polar function. So we have the polar equation, the f of x equation be a polar function, excuse me, in the polar coordinate system for 0 to 2 pi, so we know how far we're looking. and we're going to sketch the graph of this. Now, I will say on the AP exam, you're not going to have to graph any by hand, but I feel like doing a little graphing by hand will help you understand how to work with the graphs and definitely how to pick the right one. So the first thing that I like to make note of is, can I tell if there's any symmetry? If there's some symmetry, then I definitely want to look at that. And so I can see, since I see the word sine right there, remember we said up here, if it was a sine equation, it's going to be with respect to pi over 2. So it's symmetric with respect to pi over 2. So I am going to add that up here in my information about what I know about this graph. So I know it's going to have symmetry at theta equals pi over 2. So what does that mean? That means when I'm looking at my graph here on my circular graphing system, here's the pole axis, here's pi over 2. That means I'm going to have symmetry that runs down like this. So you can use that to not necessarily have to calculate everything. And this is the pi over 2. So the things that are on this side are going to be symmetric with respect to the stuff that's on that side. So that's the first thing that I want you to be mindful of. The second thing is I want you to realize we're going to graph all of these points. And some of them are going to be easy to calculate and some of them aren't. If they're not, then I want you to use your calculator, okay, to do the calculation. But we are going to set them up. And I want you to practice a little bit of looking at this and thinking, what could I do by hand without needing a calculator? And what angles am I using when that happens so that I can make my life easier? So if I'm having to predict something later on, I'll have an idea in my head of what would be good angles to use to work with those predictions. So we're going to start over here with the graph. We've already said we know it's symmetric with respect to the pi over 2 axis. This graph is increments of pi over 12, just like we studied when we did our points. So we're going to leave the first one blank because that would be pi over 12. And then we're going to have our pi over 6, pi over 4, and pi over 3. Then we're going to leave this one blank. We have pi over 2. We're going to leave this one blank. So now we're at 2 pi over 3. Okay, so do you see how that works? I want you to go ahead and label all of the angles back around to 2 pi of the angles that we typically use on the unit circle. So go ahead and pause now. Okay, so hopefully you didn't have any trouble labeling that. I realize I didn't get 3 pi over 2 labeled down here. And then this would be 0 and 2 pi. I forgot my quadrantal angles. Okay, so now we have all of the important pieces. So we're going to start at 0 because we're starting here at 0 angle. And then we're going to calculate all the way through all of these points. So the first thing I'm going to do is go through and write them out. And then we will look and decide what ones could we do by hand. And then we'll pause the video and do those by hand. And then we'll use a calculator to do the rest. So if you need to pause and go grab a calculator before we hit that part, feel free to do so. So what I mean by writing them out is I'm going to take 0 and substitute it in for theta. So I'm going to get 3 minus 3 sine of theta. That's what I mean by putting it in. Yeah? Okay, I am going to actually erase that and move that over so I leave myself a little bit more room in the box. But I'm going to do 3 minus 3. And when I put theta in here, I'm just going to write it on the first one so we have 1 in our notes. So that's sine of 0. And so then I'm going to calculate it. So I'm going to say 3 minus 3. And what is the sine at 0? The sine at 0 is 0. So now I have 3 minus 0, or 3. So my theta is 0, my R value is 3. So I'm going to go set the theta is here, and then I'm going to go down 1, 2 to get to here, 1, 2, 3. And so that's going to fall a little between right here because that's where my 3 would be. And I'm going to have this point right there. So that's our goal as we go through this. So as I'm doing the next one, I'm not going to write this step down. I'm just going to go straight here and get an answer. So I'm going to say 3 minus 3 times, and I'm going to get pi over 6 here for theta. Pi over sine of pi over 6 is 1/2. And so I'm going to get 3 times a half and 3 minus 3 times a half. So that's going to give me roughly 1.5. So that's a second box that I could easily do in my head. So now I'm going to do pi over 4. So I'm going to do 3 minus 3 times. what is the sine of pi over 4? That's root 2 over 2. And so when I'm calculating that one, that's going to be a little more challenging, right? Because this 3 and 2 don't simplify. So I'm going to have to get a common denominator, some things like that. So we're going to save this one to be a calculator problem. So as we go, the ones that we become easy to calculate with, I'm going to highlight. And the ones that are going to be more of a calculator type calculation, not that you couldn't estimate it, but we're not going to right now. We're going to work on just kind of recognizing which numbers have patterns that tend to be easy to compute. Okay. So what I want you to do is pause your video and I want you to go through, and anything that you can easily do. Anything like this, you're going to leave unhighlighted and you're going to come back with your calculator and do that problem. So let's do one more together. So we're going to do 3 minus 3 times the sine of pi over 3. The sine of pi over 3 is root 3 over 2. And that one's going to be one that's a little more complicated to do by hand. Moving on to pi over 2. So then I would say 3 minus 3 times what is sine of pi over 2. Sine of pi over 2 is 1. So we can see that one's pretty easy to compute, right? 3 times 1 is 3. 3 minus 3 gives me a R value of 0. All right, so hopefully you get an idea. I want you to go ahead and fill in the rest of your table, and then I want you to go back and highlight any ones that turn out like this, which are easy to calculate in your head. Okay, does everybody understand what we're doing? All right, then go ahead and pause your video and complete the table. So how did you do so far? So I've highlighted all of the ones that had pretty easy numbers for me to work with. I think you can see most definitely all of the quadrantal angles were very easy to work with. Look at your 0, your pi over 2, your pi, 3 pi over 2, and 2 pi. But that's not going to be necessarily enough points to be able to do a good solid polar graph. So then you're going to look at what numbers and angles am I using that are going to be easier to work with, because we know that the coordinates of pi over 3s and pi over 6s are either root 3 over 2 or they're 1/2. So as you can see, the other ones I have highlighted here are the 1/2s, because when I take sine of pi over 6, that gives me 1/2. So all the multiples of pi over 6 are going to have that 1/2 in them, and that's going to be a little bit easier to calculate with than the ones that have root 2 over 2 or root 3 over 2. And so that's a little backwards from some of the other things we've done, because oftentimes we use the pi over 4 angles because they were easy to work with. But in this case where we're calculating, it's actually going to be the quadrantal angles and then which of the coordinates can give you the 1/2, depending on if you're doing pi over 3s or pi over 6s, and whether you're doing sine or cosine. So those are kind of the things that we're going to do to help make this a little easier on us. Now, what we're actually going to do is we're going to plot this on our graph. And remember that we said graphs go counterclockwise. So we're starting over here with 0 angle, and we counted out 3. So now we're going to go to pi over 6, and we're going to count out 1/2. So when we do our 1/2, we're 1/2 units down this line. All right, so what I want you to do is go ahead and pause your video and actually punch in these that we don't have highlighted on your calculator. I'm going to write mine down to 4 decimal places just so you can see rounding and stuff like that. But if you just go out 3, that should be good too. And then we'll come back together here in a moment and we'll plot all of the points in the table. So pause your video now. Okay, so now we are going to plot these points on the circle. Now you will have to do a little bit of estimating, like 1/2 on the pi over 6. So remember we said we go to the pi over 6 and then we're going to do 1/2. So I think 1/2 is going to be like, meh, right in, I lost my line. This is 1 and like a half more, maybe right in here. It's a little bit of estimate. I'm not exactly super thrilled with the way these are marked off, but we can make it work, right? Okay, so what do we know about symmetry? We know that if this is our line of symmetry, if we have this point here, we're going to have another point mirrored over here at the same point or same arc, okay? So keep that in mind, and as we start seeing that the points that are mirrored, then we can not have to calculate. We can just go over this line and plot that point. but I just want to plot a few to start with. So then we're going to go down to pi over 4. So now we're on the pi over 4 line. So we do that first, and then we're going to go down about point 0.9, let's say. So not quite at 1. And so at pi over 4, there's my pi over 4 line here. So we're going to go down, let's see, probably on pi over 4 line about here. And then we're going to go on to the next one, and this one is pi over 3, but it's at 0.4, so it's even closer. So 0.4 is going to be down in here. And then when we get to pi over 2, the line of symmetry, it's at the pole or right here at 0. Okay, so that's kind of showing you how that works, and then we can mirror these points over here. But let's just keep going for now. So now we're going to go over to 2 pi over 3, and that's going to be 0.4. Can you see how over that line these points mirror, and these points mirror, and these points mirror, and these points mirror? That's that whole line of reflection that I was talking about, this reflexive line, reflection line right there, symmetry line. All right, so then over at 2 pi over 3, we're going to be down here at that 0.4. So 2 pi over 3 makes me be down here. And then we're going to be at the next one, 3 pi over 4. So we're right here. We're going to go out to 0.9. So let's see, get on the right line. It's a little bit more challenging when they're in the small part down in here. So we're, it looks like, going to go over about right there. Again, a little bit of an estimate here. I like bigger graphs when I'm doing this, but that's okay. We can do it. All right, and so then when we get to 5 pi over 6 would be this line right here. We're going to be at 1.5. So then that's going to put us back up on this line. Right here, maybe. All right, so now we're moving on to pi. So at pi, we're at 3. And so we know that 3 is kind of midway around here. And then at 7 pi over 6, so now we're down here at this line, then that's going to be 4.5. So let's see, 4 is this ring right here. And then 0.5 would put it about here. And then we're at 5 pi over 4, which is right here. And then we get 5.12, so about 5.1. Okay, so you get the idea. We are right here at 5.1. I want you to plot the rest of these points on the graph. So pause your video. So hopefully you can kind of see that little dimple right in there. This is actually not that you have to know the name, but this is a limacon. And it is cardioid shaped, meaning it's shaped like a heart. There are many different kinds of polar graphs. Again, you don't have to know any by name, but we have limacons, which we can have a limacon with an inner loop. We can have a cardioid like we just graphed. We can have a dimple that kind of goes in just a little bit but doesn't make an actual point. We can have one that's convex that comes out right here. So this general form of the equation, r equals a plus or minus a b cosine theta or sine theta, produces this kind of limacon. So we have to have that plus in between. The ones that I like, I think are fun, are the rose curves, and they have petals, and you can have odd number petals or even number of petals. You can change the length of the petal by changing the a value here. And all of these kinds of equations are in the form of some number and then either cosine or sine, and then some sort of horizontal stretch or compression that happen in there. So you can make pretty rose shapes. There are circles that can happen. This is just a cosine theta. There are lemniscates that are just these little figure eights. And we can do a lot of different things if we know the symmetry, which we have on our note sheet, whether it's symmetric with respect to the pole axis or to the pi over 2. And then changing these numbers A and B, distort and change and make the shapes look different. So in our case, it is a cardioid, which is just the heart shape. So you can see we went all the way down to a point and around. This is our line of symmetry. So can you see how these points are mirrored across that line? And so you can go around your shape that you're graphing and you can do some of that mirroring. Somehow I think I got off a little bit right here. I don't think I should be have a dot there. So this kind of looks a little wonky. Okay, so there, I fixed that. So now everything is mirrored. So you can use that tool of knowing where the line of symmetry is to not necessarily have to calculate every single point that we did. I thought it was beneficial to do it right now just so you could kind of get in the habit of thinking about when is this going to be a good value to use to estimate and when is this going to need maybe a calculator because it's going to be a little more complicated, or maybe I just have to stop and think, okay, what is the square root of 3? So that's a little bit bigger than 1.5. And if I take half of that, what's going to happen to it? And then I'm going to multiply it by 3, and you can do some of those estimating things to help you out with that. So a couple of things if you're using your calculator to double check anything that you're doing is you want to make sure if you're going to graph that you turn your calculator onto polar mode, which is right there, excuse me. And then also that you're still in radians. And then when you go to your y equals, you're going to see the r equals equations. And so that's kind of all of the forms we've been talking about have r equals. And then when you graph it, you may have to adjust your window to make sure you're going to see the full length of the pedal. And then be patient because sometimes, like in this case, if you have certain numbers in the inside of your cosine or sine, it may still be graphing and repeating patterns of the pedals. And so you'll see a little wheel turning up here if that's the case. All right, just a few things to keep in mind. And as we've been talking, it's very common for polar graphs to display symmetry, so we can use our understanding now of the symmetry to construct graphs quickly and easily. On the AP exam, polar functions will only appear on the multiple choice questions. This means that you will not have to sketch the polar function by hand. That doesn't mean you won't have to if you do it in another math class later on after you get past this one. But for this test, just know you won't have to actually do the graphing by hand, but you're going to need to understand the polar function, their graphs, and what portions of the graphs exist within various domains. And so those are all some of the things we're going to be working on the next part of these. So a lot of these are multiple choice questions. We are going to create rectangular grids to help us figure out the graphs, and then we'll answer a question. So my note page that I'm working on here, it's a little bit bigger space than what you have on your student copy. But when I'm writing, I want to be able to write big enough and be able to explain things well so that you can understand what's going on. So this is the exact same, all of the questions, the rest of these questions are all the same questions. Mine are just spread out a little bit, so I have room to write you some notes and some things over there. So when we're working with multiple choice questions involving polar functions, it can be to our advantage to evaluate the function at several uh, thetas. So we need to get a semblance of that. It can be extremely helpful if you have a picture to make note of the symmetry. For instance, is it going to be symmetric with respect to the pi over 2, or is it going to be symmetric with respect to the polar axis? And so hopefully we can see that this one is definitely symmetric. Lost my highlighter there. It's the pole axis right here. So we can see everything is mirrored over that point. And then we can consider our multiple choice answers as part of a way to narrow down a problem. So the evaluating points, looking at the symmetry, and using our multiple choice options can help us figure out this graph. Now keep in mind, you're not going to have to actually graph any by hand. So these are tools to help us narrow down answer choices and to make a reasonably educated guess about what answer we think this should be. So the first thing I'm going to make note of is we said it's symmetric with respect to theta equals pi over 2. That's this piece up here. Okay, and so what that means is points on this side should have a mirrored point on this side. And then we are going to look at what that means. So if you remember at the very beginning, we said if it is symmetric with respect to pi over 2, then we know it has to be a sine equation. So knowing that piece of information then, that lets me rule out choice C and D because those are both cosine. So now we're down to 50-50. So let's look at what's the difference between the two. Choice A, we have a positive R, so it hasn't been reversed. Point B still has 3, but that negative in front means that we reverse direction. They still have the same horizontal dilation of 1/3. So then the next thing I'm going to do is I'm going to pick a point to help figure out how to narrow it down. So when I look at this point, I can see that when I'm at the pole axis, my point is at 0. So every time I'm back in here, we went counterclockwise around the pedal. We're here, then it's going to loop down here and be back here again. Then it's going to loop up here and be back here again. So at the base of each of these petals of my rose curve, we are here at the pole or at the origin. At the height of the petal, we are out here at 3. So this one's at 3, this one is at 3, and this one's at 3. Or it could be a reverse. Maybe we were here at 3 and we reversed it back over here. So all of those things we talked about when we talked about plotting points. So as we eliminated C and D with the symmetry option, you could have also calculated F when theta is 0. So for instance, I could plug in C, or to equation C, and I could say 3 cosine, and then 3 times 0 would just be 0. And then when I calculate F at 0, I get 3 times, and cosine at 0 would be 1. And so that gives me F at 0 to be 3. And according to my graph here, at 0, it should be 0. So that's another way that I can eliminate choices. In this case, C and D. So we have the symmetry option, we have plugging in some values. So sometimes it can be helpful to use both. I think symmetry is a nice, quick, easy way to kind of do some of that. So then as I look at my graph, remember this is in pi over 12 increments. So this is pi over 12. So this one is pi over 6. And so I can do some calculating and I should be able to say at pi over 6, the radius is, what's that out there? 3, right? So we can use some different characteristics to help us. I'm going to go ahead and try and see if I can eliminate B. I've already got D and C, so I think I'm going to try and see if I can eliminate B. And so what I'm going to do here is pick an angle to plug in and see what I get. So let's look at B and see what we can plug in and try. Okay, so here's my choice B. That's what we said we were going to try next. I'm picking the angle pi over 6, so I replace theta with pi over 6. So that's going to be -3 cosine, and 3 times pi over 6 is going to be pi over 2. So then I go and evaluate at cosine at pi over 2. So -3 times cosine at pi over 2, what's going to happen there, right? It's cosine sine. So at pi over 2, cosine stays put. So that's 0. And you know what, guys? Sorry, I picked this one, didn't I? I meant to do sine. So give me a quick pause here and I will change this out. So it is what I said, because what I said and what I wrote were two completely different things. Okay, I think that's pretty good there. So we can do choice B right here. Clearly says sine, not cosine. All right, so let's try this again. All right, so then I'm going to say sine at pi over 2. So cosine would be 0, sine would be 1, so I'm going to have -3 times 1, which is going to give me -3. So if I'm plotting the point, which would be pi over 6, the radius should be +3, not -3. So I can eliminate choice B now using what I know about those values. So that leaves me with choice A. And you could plug in a number if you wanted to. You could go into this and say pi over 6. So 3 times pi over 6 is pi over 2. Sine of pi is 1. 1 times 3 is 3, which does give me the r value at this point on my graph. So that's the processes that we're going to use to eliminate. Again, we're going to use what we know about symmetry. We're going to use what we know about some of the placements of the point, like this one had these 0. Every time you get back to the middle or the bottom of this petal, that was going to hit at 0. You could look for some of those things. All right, so let's see how you do. Let's give you a chance to work on example 3. Notice that we said, when we talked about how the problems were going to be set up, it said this shows the graph of a polar function, and it tells us that r is going to be f of theta for these values, and these are all my options for f of theta. And so we're going to use what we know about symmetry to eliminate answer choices, and then we'll look at what answer choices are left and see which one is going to be the correct choice. All right, so go ahead and pause your video and see if you can work through problem 3. All right, let's see how you did. So I know it was symmetric with respect to pi over 2, so I drew my line there so I could see, which means it has to be a sine theta equation. So that allowed me to eliminate C and D right off the bat. Then I tested choice A. So I looked at pi over 2 and I knew it was going to be down here at 6. You could get this inner loop by, you could have been at pi over 2 and reverse direction to get this inner loop. So I'm kind of focused on this 3 pi over 2, which is on the 6 ring right here. So that would be the polar coordinate 6 comma 3 pi over 2. This is actually a limacon with that inner loop, so it's a type of graph. Again, you don't have to know the names, but I am going to throw them out there at you so you kind of think about some of the shapes. Then I tested choice A, which was 2 plus 4 sine, and the angle I'm using for my test is 3 pi over 2, because remember from that first grid, we said our quadrantal angles could be the easiest to calculate, and then we kind of picked carefully from there. So I plugged it in, so I got 2 plus 4 times the sine of 3 pi over 2 is -1. 4 times -1 is -4. So when I combine this, 2 minus 4 gives me a -2, which is not the 6 I was looking for. So that let me eliminate choice A. So that left me down to B, and I went ahead and tested the value on this one just so you could see for choice B. So I put the 3 pi over 2 in here. 2 minus 4, the sine of 3 pi over 2 is -1. -4 times -1 is +4. 2 plus 4 is 6, which is what I was looking for 3 pi over 2 to be. So that left us down to our answer choice of B. Okay, so the last two examples we were picking and looking at graphs and matching equations. Now we have part of a graph, and we are going to try and match the right equation with your A and B values that would match this piece that you're seeing. So you're seeing from this pole, this graph that goes around this way, and when it's back at that vertical axis again, it's down here. So this is the piece of the graph we have to work from. So let's look at the information. A portion of the graph of the polar function is shown. So again, we have polar functions in the form of r equals f of theta. And this time it does give me an f of theta equation. So f of theta is right here, which is going to be -3 sine of theta. And that is shown in the polar coordinate system above, where we have a less than or equal to theta less than or equal to b. And so if 0 is less than or equal to a, is less than or equal to b, is less than or equal to 2 pi, which of the following could be the values of A and B? So the key there, which could be the value. So here is your choice. Again, you can see multiple choice. You can see we're going, even though our A's and B's are in here, we're going from 0 to 2 pi. And there are connections to A and B in terms of the different graphs that I showed you on this help sheet. And so sometimes then, you will get statements like A has to be bigger than B for these equations to be true, or, something along that lines. And again, we're not overly concerned with that or worried about you knowing that, because we're not going to be grading or graphing them by hand. But we are going to take and use tools that we already know and that we already have and that's a rectangular graph. So I am going to make a rectangular graph of this equation, okay? So as we look at f of theta, which is -3 sine theta, what transformations do you see? You can see that for this particular problem, it has a reflection over the x-axis. It has a vertical stretch or vertical dilation by 3, and it's the sine function, right? So that's what we know from the graph. So it has been vertically dilated, so it's going to be stretching up, stretching down. Hasn't been translated, but it has been reflected upside down. So I'm going to get my graph going here. And 1, 2, 3, 4, and then we're going to go up to 3 and down to -3. That's what that dilation right there in front is telling us. So then when we graph this, this is going to be pi over 2, pi, 3 pi over 2, 2 pi, and we know that it's flipped upside down. So then I'm starting, this was sine, so sine starts at the origin, so it's still starting at the origin, but instead of going up to 3, now it's going down to 3, back to the middle line, up to 3, and back to the middle line. So my graph is going to look something like this. So we have this graph. Well, what does this graph represent in terms of the polar? These points on the curve are the R values. They're the distance from the middle line, or in our case, the polar axis. So what that means is if I look at where that graph is, I'm going from that middle line down to my graph, and I can see that that distance is getting longer, and then it's starting to get shorter, all in the negative direction. So this part of the graph is negative, and it goes down, the distance gets longer, and once it hits this peak, then it starts getting smaller. And now I'm in the positive area, so this is negative, and this is positive. When I'm in the positive area, from that middle to my graph, starts small, and it gets a little bit bigger, a little bit bigger, and then starts getting a little bit smaller and a little bit smaller. So I'm going to use what I know about these graphs to come up with that. So as I look over here, I can tell at 0, I should be at the pole. And then at 3 pi over 2, I'm going to probably be down here at, what is this, ring 3? So just like we did before. So now I'm trying to figure out what part of this graph would match up with this part of my polar graph. So what I'm looking for is it positive or negative from the values that we're talking about? You could calculate some values and see. For instance, at 0, I'm going to be at the pole. What's happening at pi over 2? At pi over 2, then, I could have another part of the graph here. I could be reversing. It just kind of depends. So as I start looking at my options here, the first answer choice, here's all 4 of our answer choices. So I'm going to kind of just look at what's happening on this graph for each of these windows to figure out which one matches up. So if I start with 0 and pi over 2, then I'm looking at 0 to pi over 2 down here, and it's going to be negative, and the values are getting bigger. So then I'm looking at this graph and trying to figure out if that is going to match up. Are the graphs from 0 to pi over 2 getting bigger in the negative direction? So you could test values. Remember, we know if this is 0, then this is going to be pi over 6, and this is going to be pi over 4, and this is going to be pi over 3. And so we are kind of testing those values around to pi over 2, because remember, we graph clockwise and see what's going on. So let's just see where we start. If we start at f of 0, so I'm going to look at choice A. And so I'm going to go from 0 to pi over 2. That's what I'm kind of looking at. So these two pieces, my A's and my B's. So let's look at what's going on. So as I see these distance from where it be at the center to the curve, it's getting longer and longer until I get to pi over 2. So that means it's negative, and then the values are getting larger. So they're increasing. So when I'm looking at these values here, then what is happening, let's say, if we want to like test some values here, pick your pi over 6, your pi over 4, your pi over 3, and your pi over 2. I would definitely do pi over 2 as well. So for choice A, I tested out pi over 6 because I knew sine of pi over 6 is 1/2, a little easier to work with. And I tested out sine of pi over 2 because I would be looking for values from 0 to pi over 2. So those first quadrants. So when I did pi over 6, I got -3/2. So at pi over 6, the -3/2 would be back this way. And so that's not this piece of the graph that we're seeing. It doesn't mean it couldn't be a point somewhere else on the graph, but remember we have restricted this down to just this little piece of the curve. So we're testing choices to see which one fall on these curves. So then I have sine at pi over 2 is 1, -3 times 1 is -3. So at pi over 2, at -3, that could be a possibility, but we already ruled it out from this one. So I know that so far, for example 4, I can rule out choice A. Okay. So then let's look at, I don't know, we can do choice B. All right. So choice B is going from pi over 2 to pi. And so I know that this could be pi over 2 to pi is in this quadrant. If I reversed those r's, I could very well get these points here. But let's test a few just to make sure. So in this interval, we're going to test points just like we did before, but pick your angles over here. So pick a few and test them and see what if you can figure out if you think this might be the correct answer choice. Pause your video. All right, so as I'm going through choice B, remember we're going from pi over 2 to pi. So I tested 5 pi over 6, and 5 pi over 6 should give me -1.5. That looks like that could produce something there. And then when I look at pi, which is over here, that could give me my pole. So my 2 points right here, I tested definitely are looking a lot like making choice B the correct one. And so in choice B, we are looking at in this area going from pi over 2 to pi. So right here, we would be negative, and then at pi, this distance is getting shorter in that negative direction. So you could say, you could think about it as decreasing, maybe something like that, if that helps you with your choices. And this is, in fact, the correct answer. So we can rule out these two. You can go ahead and do the process and test for choice C or D if you wanted to see what you got. But in the essence of time, since we have found our choice, we are going to move on to question 5. Another practice with a partial graph and testing values. So notice now we're looking at this piece right here. So that's the part of the graph that we have. And when we look at the information here, we see that we have a portion of a polar graph. How about graph? That's definitely a typo that needs to be fixed. Graph. And then we have our polar function. So we're still talking about r equals f of theta. They give us a theta right here. And so notice in this equation, theta has had a horizontal dilation by 1/3 and a vertical dilation by 3. And so again, we're looking at coordinates where a is going to be less than theta, which is going to be less than b. And then 0 is less than a is less than b is less than 2 pi. So it tells us we're looking for one rotation there. What could be values for A and B. So we had a little practice graphing here. So the first thing we're going to do is get ourselves a graph of the sine or cosine function that it's giving you. And in our case, it's going to be cosine. And so we should be able to come up with a graph by hand as we're doing that. So things that you might want to keep in mind, you might want to keep in mind, make sure you know what the period is, what the transformations are, things like that that can help you choose. We know that if it's cosine, then it's going to be symmetric. Remember from the first page, so if it's cosine, it's symmetric with respect to the pole axis, all things that you could use. We might actually go back up and add that to the last problem we did, just so you have it in your notes, because since this equation was a sine, then we know this one had to be symmetric with respect to pi over 2. So symmetric with respect to theta equals pi over 2 because it's a sine theta equation. So that's just another tool we have in our tool belt to help us out with that. So let's look at some of the basics here, and then I'm going to have you pause your video and see if you can test points and figure out which one will work. So for this one, we know that it is right here, it's a cosine. And we said we know that when it's cosine, it's symmetric with respect to the pole axis. So it's symmetric to the pole axis. And that's this horizontal axis right here. And so we know that it is going to have some transformations. And so we said it has a vertical dilation by 3 and a horizontal dilation by 1/3. And that's just this rectangle. And so the rectangle type of transformations are what I'm talking about here to help you get your horizontal graph. We know that it has a b value, so to find the period, we're going to take 2 pi and we're going to divide it by what b is, which is 3. So we know our period is 2 pi over 3. So by the time we get to 2 pi over 3, we're going to see one full valley because that's what that cosine graph looks like. And so we're going to kind of look at past that probably because I have kind of this information, but we can get that rectangular graph and then see how far, if we need to extend it past 2 pi over 3 to be able to answer any questions. And it looks like we might have to because this choice goes out to 3 pi over 2. So we might need a little bit further out than that. So go ahead and get a graph, a rectangular graph for 3 cosine of 3 theta. Pause your video. Okay, so we had to do a little bit of a little more calculating to get a decent graph. So when I'm looking at the period being 2 pi over 3, then I needed to know when is it going to be on the x-axis, because if it's on the x-axis, then it's at this pole right here on the graph. So you can look from pole to pole and see what's happening. For instance, from the pole marker at pi over 6 to pi over 2, the radiuses are going to be negative and they're starting here smaller, but then they're getting longer and then they're starting to get smaller again. So you can interpret how that's going to go. So here over here is a hot mess, I know, but it's just where I calculated some values to make sure I knew. So I went ahead and calculated the zeros. We've already learned how to solve trig equations. So I said, okay, I want to know when f of theta is 0 because that's when it's going to be at the pole markers. So I set it to 0 and then I solved it for cosine theta, which gave me my pi over 2 and 3 pi over 2. And then I adjusted because we weren't just solving theta, we were solving 3 theta. So I multiplied everything through by 1/3. So I knew that it was going to hit the poles at pi over 6s and pi over 2s. So that let me kind of set up some boundaries here. Then I tested some function values to see where I was going to be on the graph till I could see what the pattern was. And I took my graph out to 3 pi over 2. And then I just looked at the length of the radiuses between, whether the graph was negative or positive, what the radiuses were doing. And then that helps me to eliminate my choices down to choice D. So hopefully you got that as well. I marked some of the angles that I was looking at on the graph and comparing to my rectangular graph. And that's how I narrowed it down. Because remember, we said we were going to use answer choices, what we knew about the graph itself, the characteristics like the symmetry, the transformations, the period, all of those things to help us answer and figure out which one of these values from A to B could give us this. Now, remember, this is just a little piece of it. It doesn't mean that we couldn't calculate points that are on an actual polar graph of this equation, but they're not the ones that are visible for us to look at. So we were trying to test points and look at lengths of these radiuses to figure out which one could produce this little piece. As we talked about earlier, we have different kinds. So you kind of have to be careful. For instance, I might be just given this little loop right here, but there's all these other points that are around on the graph that could come into play. I might only be given this little piece of a rose curve, but I could calculate points that might end up on one of these other petals. So we just have to kind of pay attention to this rectangular graph. I think that's most helpful, and we'll definitely use that as we talk about rates of change of polar graphs next class. All right, let's look at the last one, example 6. All right, so there is a lot to unpack in this problem. One, we do get a full curve graph here. So we can see a full rose petal curve. And it tells us this figure of this polar graph where r equals f of theta, which is one of the clue-ins for our polar. And they give us the equation f of theta equals 6 cosine 3 theta. They're telling us we're looking from 0 to 2 pi. And they have 4 points, A, B, C, and D marked on the graph. So A, B, C, and D. That D is a little hard to see. So it's marked on the graph. If the domain of F is restricted, so it's restricted to this right here, the portion of the graph excuse me, one more time, the portion of the given graph that remains consists of two pieces. One of these two pieces is the portion of the graph in quadrant 3. So 1, 2, 3. So this portion of my graph right here in quadrant 3. And then it says quadrant 3 from C to D. So we're looking at from C to D. Okay. And then it says, which of the following describes the other remaining piece? So when we're looking for like, is it D to B, B to D? Is it going to be D to A to D? Is it going to be D to C, or is it going to be C to D? So again, we're going to create a graph here, so that rectangle graph, so that we can kind of look at that and see what's happening in those pieces. So go ahead and pause your video and create your rectangular graph. Okay, so we have the information we know about the graph. It's symmetric with respect to the whole axis. That's this way. You can see that it matches up when you fold both ways. So we know it was going to be a cosine graph, which makes sense right here. Yeah. We know that D is at the pole. So for each petal loop comes back to the pole, each petal loop comes back to the pole, each petal loop comes to the pole. So if we want to find where this graph starts, I did f of 0, and f of 0 gave me 6. So it starts here, and then it graphs counterclockwise. So as we go with these angles, then it's going to travel through this pattern. And when it gets back to the pole right here, that's going to be at pi over 2. So pi over 2 would graph it to the pole. Then that pattern repeats. So we knew that this is the piece that we were talking about from the description. So as I worked through my values and worked through my graph, knowing this is positive and these values it starts big and gets small. In this part of my graph, it's starting small, and then those negatives are getting a bigger number, and then it starts getting smaller again, or moving up toward the pole again. So I used all of those and kind of worked my way around the graph. And then I realized that when I was calculating 2 pi over 3, it's going to give me that 6. And so that pattern of this part right here in quadrant 3 ends up being this piece of the graph right here in quadrant 2. So process of elimination to get rid of A, B, and D, settling on C is my final choice. So that was a little more challenging. You might have to kind of think about that one a bit, but these rectangular graphs are going to help considerably, and I like to draw those arrows from the center to where the graph is so that it kind of helps me keep track of what's going on here. All right, that wraps it up. Next time we're going to come back. We're still going to be looking at graphs, but we're going to be talking about rates of change of polar functions. All right, thanks guys. Bye.